So I'm going to talk about some new structures in gravitational radiation. And so we have heard a lot of interesting talks related to radiation and other fields this week. So let me first give you a little bit of a background. So where do these things come from? So we have spacetimes with radiation. The point of view that, let's say, I take, so we look at some Cauchy problems for the Einstein equations, where you look at some open set of initial data, you evolve them under the Einstein equations, and you would like to understand what happens at null infinity. That's where gravitational waves are observed. So I'm going to introduce gravitational waves and memory. So we had a really great talk yesterday by Bob Wald talking about memory and infrared divergences. So what I would like to do today is I stick with the GR, the general relativistic part, and like to present some new structures in certain type of spacetimes. So of course, as we have heard in several talks, LIGO has observed gravitational waves, LIGO and VIRGO together, since 2015 several times. And a typical source is when two black holes merge, then gravitational waves are sent out, which travel in a space-time along null hypersurfaces out to null infinity. And then we have the beautiful picture taken by the Event Horizon Telescope, which actually really closes in very close to the surroundings of a black hole. So as I said, I mean, we are really in an interesting era, I think, which is also the theme of the whole program. So we have gravitational wave astronomy, we have a lot of physics input, and we have mathematical input. So, and I think from a lot of viewpoints in general relativity, things have culminated in a really great way. I think we're living in a really great era now, that we have the tools mathematically to attack really interesting questions and even see things in detectors which have been, predicted for about a century, more or less. So, of course, we all know our good friends, the Einstein equations. There's not much to say here. Let me just say that in this talk, I will mainly focus on the Einstein vacuum equations. The results can be extended to some neutrino clouds. So, I talked about gravitational radiation, or I mentioned gravitational radiation for binary black hole mergers. So if you think that the sources are now maybe not just a binary black hole merger in relatively non-dense parts of the space-time, but maybe embedded in huge neutrino clouds, etc. So then the results I'm going to present also hold, and some extra structures come on the surface too. If you couple now the Einstein equations to neutrino radiation, that you can model as a null fluid, for instance. So, but I'm going to concentrate, because these structures are really new in GR itself, so I'm going to concentrate on the Einstein vacuum equations for the talk, most of it. So I will use some maximal time foliation here, and U is denoting retarded time, or an optical function. And typically, space-like hypersurfaces are denoted by H, and null hypersurfaces are denoted by Cu. So we look at outgoing null hypersurfaces. Maybe I just, skip that. So we take some set of initial data as usual and evolve it under the Einstein equations. And here, L and L bar are going to be null vector fields. So if I'm locally at this surface STU, which is diffeomorphic to a sphere, you can think of this intersecting space-like and a null hypersurface, then the outgoing null direction is going to be L, and the ingoing null direction is going to be L bar. So I will use this null frame to get, a null frame consisting of L and L bar, and some orthonormal frame, which is tangential to this local surface. So to give you maybe just an idea, so when we talk about gravitational radiation, obviously there's a lot of intricate structures, a lot going on locally when black holes merge, for instance, or they have a core collapse supernovae, and then things radiate out, the gravitational waves travel out to null infinity. And when we do these observations like LIGO or VIRGO, we can think of being sitting at null infinity of a space-time. And then by then, of course, some of these structures have kind of calmed down, and other structures survive and give us some really interesting information about these sources. And here, let me just introduce the shear and some of these geometric quantities that really will tell us something about gravitational radiation, which is important. So here in the outgoing null direction, you would have a generating null vector field L and L bar in the incoming, as I just mentioned in the previous slide. And of course, I can write down now the second fundamental forms, chi with respect to the outgoing null direction and chi bar with respect to the incoming. The traceless parts of these second fundamental forms are actually our shears. And the chi bar hat is in the up at null infinity, turning into what in physics people call a News tensor, basically. And the traces of the trace chi and the trace chi bar are the so-called expansion scalars. So it turns out, oh, maybe there's a typo, not in A space. I will introduce different kinds of spacetimes depending on the, well, way they decay to flat Minkowski space, how they are asymptotically flat. So for, let's say, spacetimes constructed by Christodoulou and Kleinemann in the Minkowski stability proof, you have this chi hat times r square would have a limit at null infinity, and this is all well defined. I will look at general spacetimes where this limit does not, where this element does not have a limit anymore, but underneath this leading order structure is some other interesting dynamics showing up. But the R chi hat bar will have a well-defined limit at null infinity in all the spacetimes I'm going to present here. So as I said, future null infinity is, of course, a very important object for gravitational radiation. That's really where we are sitting at null infinity. And in this talk, I'm only looking at asymptotically flat spacetimes, no cosmological spacetimes. So the data is decaying to Minkowski at certain rates. Let me cite an earlier theorem, because these are the spacetimes created here that I will look at under some different assumptions. So we have the big theorem by Christodoulou Kleinemann about the nonlinear stability of Minkowski. And so they created a set of spacetimes, for which I give you the initial data on the next slide. And I generalized this result. And the interesting thing that I would like to talk about today is spacetimes that came out of this generalization of the Minkowski stability proof. So basically, I will, in the next slide, make quantitatively clear in formulas what we are actually looking at. But in all these stability proofs, you have small data that ensures existence of a globally unique solution of which is globally asymptotically flat, and of course also causally geodesically complete. However, now I'm interested in large data because we have certain sources that we're interested in for gravitational waves, and we might even want to consider black holes, etc. So the interesting thing is for this stability proofs that the behavior along null hypersurfaces established in these proofs is basically independent from the smallness assumption. And so the global result by Christodoulou and Kleinemann was really the main construction of this kind of spacetimes. And what we are using in this talk is the more general spacetimes I've looked at. So maybe let's look at the second set on this slide before. This is what Christodoulou Kleinemann looked at, basically. So you look at initial data, which is small in weighted Sobolev spaces, and this you can write this more or less. You can write this down as initial data of the following type. So this is data that far away from the source decays to Minkowski space at this rate. So you have this 1 + 2m over r delta ij plus some tail that decays like r to the minus 3/2, and correspondingly decaying for the second fundamental form k. So in the spacetimes that I looked at, and that came out of my proof now for the 2007 results, so we have spacetimes where the initial data is just delta ij plus 0.3 of r to the minus 1/2. So we have a tail that just decays like r to the minus 1/2, and the second fundamental form correspondingly like r to the minus 3/2. So of course, in the initial, in these proofs, the data is small, but I'm going to be interested in large data. Let me maybe give you the idea why we can look at this kind of data, spacetimes, and why they give us some good insight. Here is maybe some other type of data that is, if you think of it, involved in this more larger class. And if you want to know something about, like, for instance, if you have a non-isotropic mass term or a term which is homogeneous of degree -1 here, so that's something between Kleinemann, Christodoulou Kleinemann, and my general proof. So you can plug in more detailed versions of whatever data you want to pick and see what happens when you evolve the data at null infinity. we're not going to concentrate on that so much, but let me explain what I mean by large data in this context. So as I said, these stability proofs are a really interesting construction of a large class of spacetimes, and whereas in the smallest assumption really ensured the existence of the data, well, now we can take this data and say, let's see what survives, what can we do with large data. So you can look at large data and you can say, well, we still have some portion of null infinity for which this null structures developed in these spacetimes actually hold. To see that, it's easy actually to prove in a few lines, if you like. To see that, you can say, okay, there exists a complete domain of dependence of the complement of a sufficiently large compact subset in the initial hypersurface. And so because of that, you can say, well, we do have a solution spacetime where a portion of future null infinity is really corresponding to all values of retarded time u, which is not greater than a fixed constant, for instance. So this is what I mean by taking these spacetimes, but now plug in large data, because for a portion of null infinity, we get actually some really interesting and precise information out for that. So that's what we are doing today. So you can think of the spacetimes, maybe here I will call them B or decay, etc. in the following, so that we have spacetimes of this type, but now for large data. Okay, let me maybe just say a few more words. What I call A spacetimes, this is when you plug in, instead of a little o in my original initial data, if you plug in a big O. So, I mean, now with the stability proofs, we have that for these B spacetimes, we have total finite energy, but the total angular momentum diverges. But if you replace the little o in that r to the minus 1/2 decay in the tail of the metric by a big O, then we don't have a proof that shows stability. Then the total energy is no longer finite, and there's no existence theorem for any development of such data. All right, so let me introduce some maybe components here. So what I call 3 or E3, the basis vector, is the ingoing null component in my null frame, and 4 would be outgoing. And so you just maybe need to remember alpha bar from here. So these are the wild curvature tensors decomposed to this with respect to this null frame. And I will explain along the way how things show up, but the alpha bar up to sigma will really play an interesting role. So the alpha bar is also the 1 over r decay, the component that decays like 1 over r. So if you look in the Christodoulou-Kleinemann spacetimes, you get an overall decay of the curvature components as follows. You see by the way, the tau minus is just the 1 plus u squared square root. So think of tau minus like u. So the alpha bar is the 1 over r decaying portion of the Weyl curvature, which will be related to our really gravitational field. And then we have some peeling that was recovered in the original Christodoulou-Kleinemann proof up to the r to the minus 3. And then, well, we don't have enough decay in the initial data here, and there's some arguments about peeling or not. And so Christodoulou showed if you have, let's say, further strong decay, then basically you pick up some logarithmic term here, but we're not going into that. So in the spacetimes that I considered, so we have, of course, much less decay, so much less decay for the curvature as well. So we see we have the 1 over r squared, and some decay in u components, and everything else is kind of hidden here, like the decay of leading order r to the minus 5/2. So interesting enough, there's still a lot to say. There's some interesting dynamics hiding kind of beneath these highest order terms. Maybe I don't need to show that. Let me just show you briefly the Bianchi equations. I will come back to that in a more systematic way. But remember, the rho is one portion is the of the curvature component. Let me show you here. So the rho is the 3,4,3,4 component of the curvature, and I will show you in a moment what we mean by electromagnetic component. So this is the one of the electric components of the Weyl curvature, and sigma is going to be one of the so-called magnetic components of the Weyl curvature. So I just wrote down the two Bianchi equations for these two components, for rho and for sigma. And on the right-hand side, we have other curvature components showing up, and yeah, epsilon and theta is a torsion, one form epsilon, psi bar, theta are just other Ricci coefficients. So the this will be an important, these two Bianchi equations will actually play some important roles trying to figure out what's the structure in these spacetimes locally and how do they survive up when you go towards null infinity. So let me maybe say a few words about this very slow decay of these components. So for the chi-hat and the chi-hat bar, so let me introduce some notation here to make clear what I mean. So if in this very general spacetimes we look at chi-hat, so we see that this has a leading order component that decays like r⁻³ far away. And so when I have this square brackets, this means that this leading order term is not dynamical. It does not depend on the retarded time u. So we have this optical function u, which is going to play the role of retarded time. So these components do not evolve with u. So that's a non-dynamical component. And so if I have the curly bracket, so this means they do depend on u. So the tau minus you can think of as u here. So these are the dynamical portions of these components. So one can show that for both, if you have small data or large data, you can actually compute that the structures of these shear terms, which are really important then in the gravitational wave discussion, have a structure like that, more or less. So we have all kinds of terms at these orders, plus lower order terms. And the problem that we see at this point, if I take now a limit for chi-hat, let's say r² times chi-hat, and would like this to go to infinity, so then this will diverge. And let me now in the next slide explain what happens with this kind of components. Maybe I skip that. So this slide is kind of fundamental, and the same idea or the same discussion also applies to the non-peeling curvature component. So let me take the chi-hat as an example. So now if we remember, if we take one of these surfaces STU locally, which I can think of as a hyperplane, a space-like hypersurface and an outgoing null cone intersecting. So I look at such a sphere and I look at certain geometric quantities, let's say chi-hat on that sphere, and then I want to go out with this geometric quantity to null infinity. So like this chi-hat, for instance, does not, if I take r² times chi-hat, like I write here, and I'm sitting on that local sphere, and I want to evaluate, so what's maybe I take a point on that sphere, and then I go out to null infinity, so then r² times chi-hat, when I let r go to infinity, obviously this is going to diverge, so that does not have a limit. But we can do something else, so I can take, let's say, one outgoing null hypersurface Cu, and I take one sphere, let's call it Cu, so one local sphere, I'm sitting on this local sphere, and I can look at what happens there, and then I go on a neighboring null hypersurface and take the corresponding sphere, Cu0, so I have two hypersurfaces, Cu and Cu0, where u and u0 are close to each other, but not the same, and I can say, oh, let me look at the difference of this geometric object for the values on Cu and the corresponding point on Cu0. So when I take this limit or this difference does have a limit at null infinity. And the limit we can write down as follows. So if I take the the derivative basically with respect to u, if you like, in the 3 direction of chi-hat, and I integrate that from u0 to u with respect to the dynamical parameter u or u prime here. So then the difference of these values tends to exactly that limit at null infinity. So things are fine from that perspective. There's still something interesting to be seen, whereas the leading order components don't have a limit, at least on neighboring spheres or neighboring cones. I find that the difference of the corresponding values tend to some limit. So what we get there is then basically, well, the leading order components, like for the chi-hat, the r⁻³ decaying component is actually non-dynamical, so it does not evolve in U. And something similar can be said for all the non-peeling curvature components in this space-time, that so basically we take off, if you like, the non-dynamical part, but underneath there's a lot of interesting dynamical structures that we will now investigate. So this is a kind of a crucial point for these structures. So out of this old proof, I can say that, of course, some of the obvious curvature components tend to some limits, like r times the alpha bar, which is decaying like 1 over r and beta bar. So they take some limits at null infinity, but not the rho or sigma as before, but we'll see that something interesting can be said. So the chi-hat bar does have a limit, and let me call the limit of -1/2 r times the chi-hat bar. Let me call this psi at u. So this is, and we do get some relations out at null infinity. So we have some points here. So here, let me explain a little bit more. So let's go back to the Bianchi equations. And I'll just give you a schematic picture of what happens at the level of the Bianchi equations. So we'd like to rho, which is a electric component, and sigma, a magnetic component of the Weyl curvature. So they do not, rho and sigma do not have limits at null infinity. However, if I take the Bianchi equation, I take a derivative in the 3 direction, right? So that's the Bianchi equation. Then I get a lot of interesting structures on the right-hand side. And so let me maybe just introduce some names before I go into what is exactly behind here. So it turns out that if I take the Bianchi equations, I have the rho 3, so which is the 3 derivative of this non-peeling component. So there will be some terms coming over to the left-hand side, which will cancel out with the badly behaved terms in these curvature components. Let's call them maybe badly behaved, because there's nothing nice to extract here. However, on the right-hand side, so we'll have some cancellation on that level. On the right-hand side, these are terms that will impact gravitational radiation. And not only, so there will be extra structures than what we have seen, for instance, if we have spacetimes that decay like 1 over r. So I'll have something to say about that in the next few slides. But so for the very general spacetimes, there will be kind of different structures showing up from the curvature and also from the shear at different levels. Well, for the shear, it will be finite, but all right. So here, also one can show then that basically some structures that will show up have limits now. And so I want to take the Bianchi equation and take a corresponding limit to null infinity. And I will come back to what I wrote here. But the idea is that some of these structures here on the right-hand side, they all have some nice limits at null infinity. So this can be what this is well defined. I go out to null infinity, and then we have to see what happens on the left-hand side. All right. So let me say a few words about gravitational waves. Maybe, I mean, this is a specialist audience, of course, but I like to think about this always. We have some source, obviously, that is evolving on their own time-like curves. And during a very short period, they're sending out gravitational waves, maybe in a binary black hole merger, for instance, and these waves travel along these null hypersurfaces out to null infinity. So at null infinity, this is just a schematic picture in some sense. So we observe gravitational waves out here. And how does, let me now bring, the next slide brings some very well-known geodesic or Jacobi equation from geometry into the laser interferometry geometry. So in a laser interferometry geometry, I mean, in LIGO, for instance, we have 3 test masses, which are actually mirrors suspended by pendulums on one picture here, that are configured in some L shape. And by laser interferometry, LIGO or VIRGO are measuring the distances, the exactly very precise distance of these mirrors with respect to the initial mirror and etc. And so here is a schematic picture of just test masses. And when LIGO detected gravitational waves in 2015, and then LIGO VIRGO observed several gravitational waves from binary black hole, binary neutron star mergers. So what happens, what we have seen already in all these interesting pictures is, well, for a fraction of a second, for instance, so the gravitational wave packet comes through, the curvature of the spacetime is changing, and we see that these test masses move. We think of them as marking geodesics of the spacetime, right? So if we think of this as the spacetime, these are just marking where the geodesics are, and basically you can write down this motion as on Earth, for instance, like the Jacobi equation. So you have the Jacobi equation, which governs the motion of these geodesics, which we can actually follow as this with these test masses. Now, let me introduce now also what we mean by gravitational wave memory, as Bob explained very in a great way yesterday. So what we have seen so far is the gravitational waves themselves. What is predicted by general relativity is that there is another effect called the memory of gravitational waves, saying that where during the time the gravitational wave is going through the detector, there's another effect, which is actually a cumulative effect going on at the same time, like a accumulating effect. And this will result in the end in some permanent displacement of the test mass. So basically, the test masses will go back to rest in general, but they will not be at the same original space place as before, but they will be displaced. Of course, this is way too big here, but I wanted to make sure that you get some displacement with respect to before of the test masses. This is what we call memory of gravitational waves. So maybe let me mention also, of course, a big breakthrough were the measurement of gravitational waves, and I think which earned the Nobel Prize to Ray Wise, Barry Barish, and Kip Thorne, and all the people, of course, were on it that worked for LIGO. So I think it's a great accomplishment that after a century of thinking about gravitational waves, we are able to see them. And not only is this a great accomplishment for GR, I think it's the beginning really of a new era where we can really see deeper into the universe and really find more structures and physics in that sense. So let me go back to the memory effect and just very, very briefly give you a few names. And I apologize, I cannot be very comprehensive because the field has really grown tremendously lately. But let me mention, let's say, the pioneering names. So in the 70s, Seldovich and Polnareff looked at the linearized version of the Einstein equation and found that there's actually this memory effect. And then in 1991, Christodoulou looked at the fully nonlinear Einstein equations and realized, hey, there is a memory effect which is actually bigger than what people expected. Well, nowadays we know that, so like Garfinkel and I have shown that these are two different types of memory. So this is still memory, which is the same thing, but what's the memory going back to Seldovich and Polnareff, so we call it ordinary, so is related to what I'm going to explain in a moment, some change in a component of this rho of the electric part of the Weyl curvature. And the null memory by Christodoulou is really related to fields radiated to infinity. So this would be the shear will come into that. So there's a lot of interesting pioneering work, such as Tambour Blanchet, Thorne, and many others who actually had pioneering work in the early days. And I would like to point out the paper of 16 by Lasky and collaborators, where they suggest to detect gravitational wave memory with LIGO by stacking events. So that's an interesting idea. And lately, there's been a wealth of information, including, Bob Wald, whom we heard speak yesterday, and many other people. So let me just say you can look at gravitational wave memory and find some contribution from all kinds of interesting stress-energy tensor we couple. And also with Garfinkel, we found that we have, in the pure Maxwell equation, we found that there's actually an electromagnetic analog of gravitational wave memory. So there are two analogs of this memory effect. So let me now say just very briefly what we mean by memory and go into the deeper structures. So again, so if you think of the Jacobi equation, then you think, okay, we can integrate the Jacobi equation twice and we get some distance on the left-hand side. So this is exactly what we do, and I call this delta x. This is this distance which will be a permanent displacement of the memory effect. So that's a distance delta x. And on the right-hand side, there's, of course, some curvature terms, but we'll see that with some relations on the right-hand side, what we get out, there's a geometric object. So this d0 here is just the initial distance between the test masses. R is the distance from the source. And this object here, if we are in space-time like Christodoulou-Kleinemann constructed, or if you have a decay of at least 1 over r of the metric towards Minkowski, then this right-hand side would be exactly the differences of the other shears, the chi-hat at null infinity, the corresponding limits of the r squared times the chi-hat at null infinity. However, well, and also let me say, if you have fall off like 1 over r, there's only these two types: the ordinary memory, which is a change of the electric portion of one electric component of the Weyl tensor, and the null memory, which is sourced by energy radiated to infinity. This again includes shear and energy momentum tensor. So what I'm going to show you now is that if you generalize the space-time, so for a very, very slow decay, there's a lot of else that shows up. There's some new structures, and especially we don't, so certain things keep growing. So let me say something about that. I keep mentioning electromagnetic part. So this is actually a big question when we talk about memory. So let us recall what we mean by electric magnetic decomposition of the wild tensor. We know that the wild tensor of our spacetime we can decompose into its electric and magnetic part like this. So EAB would be the electric components and the HAB here, the magnetic components. And if you like, if you write down the Jacobi equation in this very simple notation, then you will have two derivatives on the left-hand side of this delta x. On the right-hand side, what shows up is actually an electric component of the wild tensor. And in my notation, so remember from before, so if you have now the normal component of the electric part of the wild, this is what we call rho in our notation. And the sigma is the normal component of the magnetic part. So electric is rho, magnetic is sigma in this talk. All right, so if we think now of of the traditional sources, of course, which are important, but which decay like 1 over r. So we have just seen that, or let me I summarize that there's these structures that only electric parity memory occurs. There's no magnetic parity at all. And also we have the structures that I just said is one component of from the electric, from rho, the electric wild curvature, and the stress energy plus, the shear, the News tensor, which gives you an addition to the null memory. So new is that in spacetimes, when you relax really to very slow decay, like r to the minus y1/2 in the initial data, so then we get suddenly we get magnetic memory that occurs naturally in these spacetimes. Moreover, a lot more structures that start diverging. So let me maybe say a few words. I think we're going to share these slides later so you can read it up maybe after the talk. But it's interesting that Satish Chandran and also Bob Wald had an interesting, unusual example of stress energy. They with an expanding shell that they looked at in a linearized gravity that would generate ordinary magnetic memory. Also, Madler and Winnicor looked at some linearized setting, and so put in by hand, if you like, an incoming homogeneous source-free gravitational wave. So that would also give you some magnetic memory. So what we do here, I don't put in anything by hand. So I look at the pure Einstein vacuum equations with data as we have seen, and I let it evolve in time. And what comes up is that in the evolution of this data, we will have a natural magnetic memory coming out of it. Okay, so maybe a few words. Okay, I don't have too much time. Let's go here and derive the two types of memory. So for the electric parity memory, we're going to back to the Einstein, to the Bianchi equations, and there's no Ricci curvature because we're in Einstein vacuum. So rho, remember, is the normal component of the electric portion of the wild curvature. And now I look at how do these objects behave in these more general space-times with very slow decay. So what I call here lower order terms will actually just decay to zero much faster, but I will have the rho 3. So this is the derivative in the 3 direction of the wild curvature rho. And then I have this component, the divergence of the beta bar curvature. And then I have this chi hat times alpha bar. So when I look at that, I have a nice r to the minus 3 behavior of this beta bar curvature. But I have some really ugly behavior like only r to the minus 5/2 of this object. So I can do a little computation and get a little bit more out of the second object. When I do this computation, I have one term which turns out to be better. That's the trace chi times chi hat bar squared with a constant. So that turns out has also a nice r to the minus 3 decay, but I still have a badly behaved term, which is the DDU of the two shears, the chi hat times the chi hat bar. So what we do, we throw this on the left-hand side. So basically, we throw this on the left-hand side, and from the investigations of these more general space-times, we know that the right-hand side now is well-behaved. So at least it has an r to the minus 3 decay and a u to the minus 1/2. So there's all kind of data here, which is not so nicely behaved on the left-hand side, but this cancel out by this equation and the structures on the right-hand side. So now we can go and actually take limits at null infinity of this equation. So what we will do, we will multiply this equation 41 with 3r to the 3 and take the limit out to null infinity. And by doing that, let me introduce a bit of notation. So for the left-hand side of this equation, I call the limit, the corresponding limit that we take here, P3, and we will integrate these limits with respect to retarded time U. So this will give me my, what I call here P. Of course, you get some constant when you integrate, but these will cancel out later again. All right, so this equation multiplied by r to the 3 and take it out to null infinity, then what we obtain is an equation number 44 with exactly these terms introduced. And the beta bar has a nice limit, the psi has a nice limit, etc. Now, let me say maybe a few words about this P structure. So the structures in P, when we look at that, which comes from all these terms, so there will be some cancellations of the worst terms, obviously, but there's not some new stuff coming up. So what I call here again, I have my notation of the curly brackets, meaning so these are terms that show up in this in P, which have a behavior in U like the following. So there will be terms that will be growing like the square root of U. The tau minus is again like retarded time U. They will be growing like some U to the beta, where beta is between 0 and 1/2. And these will actually originate in the Weil curvature. There will be some extra terms where also Weil curvature attributes to this, but also there will be some terms that will come in from the shear. If you have stronger decay like 1/r in your space-time, I mean, the initial metric decays far away like 1/r, so then you don't have this behavior at all. First of all, you have all finite limits. Everything is finite. And second, you don't have contribution from the shears. So now let us integrate things with respect to the U direction at null infinity. And I introduce again some new notation. Maybe that's not that important at this point, but what I call here chi3 is just the limit of this object here. And I integrate again correspondingly. So we integrate the limiting equation at null infinity with respect to retarded time. And what we get basically is this equation I call 50 down here. So this looks kind of simple and nice, but let me say that there is some interesting structures hidden behind all that. Before I go and tell more about this, let me maybe jump very quickly to the other equation and talk about magnetic memory. So what we did for the electric part, we can do now for the magnetic memory. And what is really new here is that if you have space-time decaying like 1/r basically, then you don't have any magnetic memory at all. This is all 0 up at null infinity. I mean, the contributions, I mean. But let me do the same procedure for this Bianchi equation for the magnetic portion of the Weil curvature. And we can see that some lower order terms, again, when we look at this space-times decay fast enough, and we get a similar equation I call 52 here, where I have now the curl of beta bar equal to some terms on the left-hand side, where we have the 3 derivative of the magnetic part. So again, because the right-hand side is nicely behaved, I can do the similar procedure. I want to multiply this equation by r to the 3 and take the limit up to null infinity. And you'd like to understand again what are structures that will show up. So correspondingly, I call now the left-hand side, I call this limit I obtain for the left-hand side Q3. I integrate with respect to retarded time and obtain a quantity Q. So number 55 is the limiting equation. That looks very simple when we do that out to null infinity. Let's now look at some structures in that Q when we integrate that now with respect to retarded time. So we do the same thing, and we find also in this Q itself, this is now the magnetic, this is the portion which is related to the magnetic part of the curvature plus, well, the shear terms. So we get some increasing terms, which increase like square root of U, same picture more or less, but now we have magnetic curvature and some finite contributions I plug into F. So we can also derive what I call here 58 equation. And again, there's all kind of interesting behavior now behind that. Let me maybe in the last maybe 2 minutes or so explain some of these structures. Remember this slide that I showed you for the chi-hat that didn't have a limit at null infinity. So something similar we can think of happens here in the following way. So all these Q terms that I mentioned, so what I call here Q sigma 1 plus, so these are terms that originate from this left-hand side of the Bianchi equation, which originate in the magnetic part of the curvature tensor. And they will grow like square root of U. Then I have also other terms which grow at lower order, but still grow. And then I have finite terms which are rooted also in the magnetic part of the curvature and in the shear terms. So let's look at the behavior of these Q terms as well, of course, then as the right-hand side of this equation. So we are now out at null infinity, right? So we are sitting on one of these spheres S2 for a fixed U0 at null infinity. And we can consider Q at U0. So this will have a nice value. So this is a finite value at the fixed point on such a sphere Q U0 out at null infinity. Now, if I take a corresponding value, maybe U naught equals to U0 just a little bit further away, then I can look at this difference of QU and QU0. And of course, this is still going to give me some finite value. But if I keep U0 fixed now, and I let U tend to either plus or minus infinity, then this difference, this Q of U and minus Q of U0 is no longer finite. This difference actually grows with square root of U. This is what I mean. We have some growing memory. And of course, correspondingly, you can do the same thing here for the right-hand side. So this is what happens. And so there's, interesting enough, there's all these structures showing up from the magnetic part of the curvature, as well as from, there's an interesting also finite contribution, of course, from the shears. There's no shear contribution if you look at 1 over r decay of the metric at all. So, and also what we have here in 59, if you look at the more traditional sources like 1 over r decay in general, this is all 0. The new structures really show up as soon as we go. We let this beta be just epsilon, if you like. They show up. It's like a threshold you cross, and we can go. I mean, this has been shown now for up to 1/2. So this is really up to 1/2. So what we have really is that we have if you look at the divergence of this object, so these are equations on the sphere at null infinity, right? So these are all equations on such a sphere. And I can write things as follow. I have this equation for the divergence of this object, which is related to some function phi and some function psi. And the function, the Laplacian of phi is fulfilling this equation 62, whereas the Laplacian of psi is fulfilling this equation 61. And let me now again say, so if we are in all these traditional spacetimes with faster decay, then 61 is completely 0. There's no contribution from the curl equation. So we have a pure contribution from 62. Moreover, there's only one term in this P component in the ordinary memory, and just some specific term, the shear, in the F, in the energy radiated away. So what is new here is really that, okay, I'm finishing, so that we have magnetic memory, which emerges out of the Einstein vacuum equations in a very natural way, which again, if you cross the threshold of this 1 over r decay, it disappears. And moreover, interesting enough, so we have all these very different terms from the electric and magnetic part contributing to the memory, and these parts grow with square root of u in the sense I just explained to you of these differences of the Q term at null infinity. So we have new magnetic type memory, that's a new thing, and we have these growing terms, which is really an interesting fact, I think. And now maybe just the last slide, or second last, you can generalize that all to Einstein null fluid equations, where you want to describe radiation from neutrinos. With the same geometric growth, there will be a term that contributes to the electric memory from the stress energy at the same leading order divergence, square root of u. And if you go to the very ultimate spacetimes, like what I called A spacetimes, if you have a capital O decay of r to the minus 1 in the metric initially, then you even catch up another curl term in the magnetic memory, which is not there otherwise. Okay, maybe I stop here, and let me thank you very much for your attention. There's a lot of interesting questions out of that, but maybe rather than me formulating them, let me ask you if you have any questions. Thank you so much.